Hey everyone, I'm going to talk about ray tracing in radv. Um, I happen to call it world's slowest ray tracer. Hopefully we're not actually that slow, but I wouldn't be surprised if we come close. I'm going to give you a short intro about what ray tracing actually was again, but not going to talk that much about the API level. Jason had some good talks in the previous year, so watch those if you want to know more about the API level. Um, but yeah, ray tracing, like in traditional rasterization, like you take a piece of geometry, say a triangle, and you look like, okay, where does that land on my screen? And with ray tracing, you kind of can work the other way around. You pick a ray, for example, the ray you go out of your eye as you see your screen, and then see, okay, what geometry would I actually hit? And the fun part is you can do it directly out of the camera, but you can also do more ways. So you could go, for example, hey, I see a person, and then from the hit position on that person, you could go to the sun or another light, and you can do lots more ways. And that gives like way to do way more advanced lighting. And yeah, how do you trace array? And you could try to check all triangles or all the geometry, and it may be not no surprise that that's going to be pretty slow. So obviously people found a tree structure for this, what we call a bounding volume hierarchy. So basically you want to try to build a tree out of your geometry where like every node has a bounding box, an axis-aligned bounding box assigned to it. So then if you walk to that tree, like, and you see, hey, my ray doesn't intersect with that bounding box, I don't need to look at the subtree. And that can speed up things a lot. Turns out that typically doesn't make it fast enough for real-time usage, say, in games yet. So a lot of vendors have been looking at, hey, can we do a part of this in hardware so we can actually use it in games? And I'm going to look at, hey, AMD has RDNA 2 now, which has a bunch of hardware acceleration, which we've been working on with radv on enabling. So how do you do this on AMD hardware? And there's basically a single instruction that gets added. You have a node in your tree, and you can see, does it intersect with the array? And it does provide some nice bits, like if it's an internal node, uh, it basically it returns, hey, which of the children does it hit, and it gives you their IDs in a sorted manner. So like you get a nice benefit of looking for the closest hit first. And in the triangle node, it like pre-computes the barycentric coordinates. But overall, it's just, hey, we process a single node, nothing more, nothing less. And with that comes a bunch of like predefined hardware nodes. So every vendor is different in this. We have a triangle node, which actually can contain 5 vertices, and we can do 4 triangles based on pointer tagging in the low bits of the address of the nodes. Same pointer tagging is used, by the way, to distinguish between internal nodes and triangle nodes. And then we have internal nodes, both 32-bit float and 16-bit float variants. So we have 4 children per node, and min and max bounds per child. And yes, as said, it returns those. And my understanding is that roughly like it can do 1 node per compute unit per cycle. And with triangles, that means only 1 triangle. You can't test all 4 of them at once, sadly. Yeah, so how to trace array in RDNA 2? And the answer is basically just the software answer, and we replace the bit that's actually checks for the collision with this hardware instruction. But otherwise, like the tree walk all happens in shader code. So we basically have a bunch of giant near builder code of like a couple hundred lines that's yes, I see someone laughing here. I think at this point, the near builder for all our ray tracing is like by far larger than all our other meta stuff combined. So we've been taking some care recently to move at least a lot of the older stuff, not the ray tracing itself, to GLSL. We already had a GSL dependency because of the HUD that was included in Mesa for Vulkan. So that was an easy add. But yeah, we just do depth first search. And of course, at depth first search, you either need a stack or you need some backtracking. And backtracking, like we have 4,000 per internal node. So and it's sorted, so we don't have a predefined order of visiting things. So if you backtrack, you need to figure out, hey, what's the next child? And with the sorting, it turns out the easiest way to go to the next child is to do the intersection test again and just get the next child of that list. The problem with that is now you're doing 2x the intersection test. So ideally, we keep with the stack. We have two options for the stack on AMD hardware because like requirement is basically you want independent indexing per invocation, so you can't do it on registers. So we have VRAM and we have LDS, which is our version of shared memory. So no surprise, LDS tends to be faster memory. But of course, when we do that, we hit occupancy limits of like, this loop is going to be very memory instruction heavy. Memory instructions have high latency. You want latency hiding. But if you use a ton of shared memory space or a ton of registers, you can only run so many shaders per compute unit. So like you can't do any latency hiding. So like if we actually experiment with the number of stack entries, like if we want to cover like the full depth of a perfectly balanced tree, we would need 79 stack entries. And that's like half the performance of only using 16. So obviously we want to use 16, except that's basically using it is not going to be good for correctness, which tends to be a requirement. So what we kind of do is a mix short stack plus backtracking. So 16 entries in the stack, and then we backtrack if we underflow, and we try to keep the most active 16 entries in the stack. So like the top of the stack is where you're most active. So we just like as we need to grow the stack, like we just drop stuff out of it, and then we notice, hey, we've dropped stuff out of it before we start backtracking. And some benchmarks show that like now we have to backtrack like less than 1% of the iterations, which seems to be pretty decent overhead-wise. And the bonus is we have absolutely no depth limits on our BVH tree. Like previously I said 79 for like your perfectly balanced tree. Depending on how you build your BVH, like there's no guarantee on your depth at all that's useful, unless you do interesting things. And because this is a single instruction, we could actually just implement that instruction in yet another bit of near builder and get legacy GPU support. I think this basically works on all GPUs that radv supports. Some of them may not be particularly useful. Things will run on your Vega APU laptop, but it won't be pretty. And roughly half perf is actually not too terrible. Actually shows nicely like what kind of benefit we get from the hardware acceleration. And then next step is building a BVH. Like as you might have surmised, like basically any tree we can make a BVH out of just by calculating bounding boxes. But that doesn't mean it's a good BVH. Like if every bounding box is basically your entire scene, it's going to be totally useless for making your ray trace faster. And that's roughly what we did. We just took the geometry in API order and then just linearly added in layers the nodes, which probably is the worst BVH building method out there. It's pretty nice because, hey, it guarantees that it's perfectly balanced. it guarantees that it's very easy to do because like it isn't really dependent on the data, only on the number of nodes. So you can basically say, hey, I do these layers in independent compute dispatches. I know how many layers I'm going to have, and then just a barrier in between them, and I'm going to build everything. So it was pretty easy to code. Um, of course, surprise, surprise, this doesn't pass CTS. And a great example is like if you have two things next to each other which are on completely opposite sides of the scene, you just get a maximum bounding box and you get to visit all the geometry anyway, which ends up pretty badly. So we actually ended up sorting the triangles first before building the tree. So like on the center of the bounding box of the triangle. And now you might ask, how do we sort? Well, Morton codes. Some of you might actually remember this from your texture tiling, where it's a pretty common technique. So if we have multi-dimensional coordinates, and yes, we need integer coordinates, you can do that by like taking the fraction of the bounding box of the total scene. And then we can interleave those bits in a way that you kind of get an octree-like behavior in the bits when you sort. And just that sorting actually results in something that doesn't time out your GPU when you do stuff. So that is the BVH building code that's currently upstream in Mesa for radv. It's kind of, for people that are more familiar with BVH, this kind of like a linear BVH, poor man's linear BVH, because we don't do the tree building part of it. And we actually see that it's significantly worse than what's possible. So I've been playing around with profilers with a decent set of other drivers for this hardware. We're lucky to have that. And what you can see is that roughly we visit 2.5 as many nodes as a competing driver, which, like, no matter how good we make our traversal loop, that's not going to beat them. So we've been working on like optimizing this and getting stuff in. And as I said before, like a big part of this is you really don't want these complicated algorithms in NearBuilder. So we've been moving this over to GSLang, and we have some experimental stuff. It's not ready for prime time yet, as we currently, most of it is very experimental and limited in parallelization of the algorithm. So you can, like, that's also a bottleneck. How expensive is it to build this, as potentially part of it you do every frame and stuff. So we actually get pretty close. Like, I tried out 2 algorithms, and we have implementations that get roughly within 15% of the iterations. Obviously, needs to land. And surprise, surprise, we're not the only one who built BVHs. Intel has code to build BVHs in their upstreaming of ray tracing support. And Jason did a whole talk last time about how they had this interesting thing of basically doing logic in command buffers. And sad to say, we can't on AMD. Our command buffers are fairly limited. And recently, actually, like I think 2 weeks before this talk, AMD open sourced their stuff. And we actually had a big discussion about this because obviously it's very suitable for hardware because it's the same hardware. It's written in HLSL. It looked like they had some initial bits to compile the HLSL with GSLang, which would have made it an obvious choice, like try to hook it in verbatim. Obviously, we figured out that wasn't possible, mainly because GSLang just sucks as HLSL. It's very incomplete, and the recommended path these days is to use DXC. And then we went to a bunch of people and asked, like, hey, is DXC actually an appropriate dependency for Mesa? And the consensus seemed to be no. So that limits things. And then you have the consideration of we could try moving this to GSL, but then you get like, hey, obviously, if you're going to rewrite this in another language, there's going to be bugs. If you're going to rewrite this, then people don't actually know the thing they're working on, so they need to build that. Like, we might as well do something ourselves. I feel we walked in the not invented here trap very, very easily here. Then again, I don't see any great other way at this point. And then I'm going to talk a bit more about the API side. Like I talked all about ray tracing and how to build the BV8. I'm not talking about how an app uses it. So yeah, how to trace rays. There's actually two Vulkan extensions for it. The easy one just provides you a GSL object, a ray query X, and then you initialize it with the ray and some parameters, and then you say, trace me a ray. It can return in the middle of it. So like for non-opaque objects, you can do stuff like, for example, hey, if I want alpha-based transparency in like plants or something, you can decide, hey, do I want to skip this intersection or not? And then in the end, you get some results in the objects, which is like API-wise fairly simple. We have a shader loop that we have in NearBuilder. We can just, hey, take every call of trace array and insert that NearBuilder code in here, and we're done. Very, very easy. Now the messy part. There's another extension that's about ray tracing pipelines. And the idea here is that instead of just doing it synchronously, basically we work with callbacks. So like there's a raygen shader at the root, like which is a new shader stage. It calls trace ray, and then when it hits a triangle, it's going to call a new shader for the hit. You have a binding table, so we don't have one stage of every type. We have a lot of them. Like you can have a ton of stages when you create a pipeline, and then after you created the pipeline, you can get a descriptor for all of your stages, and then you can create a binding table out of them. And what you can do is, for example, the binding table gets indexed on, like, for example, your geometry ID. So this is how you can do like a different shader for like different materials if you hit different geometry. And to make things more complicated, it supports recursion. We all love recursion on GPUs. So Intel had this pass for their ray tracing support that slower shaders in near to continuation passing style. So like if you have a trace ray, you add the shader there, do some spilling and stuff, and then have a new resume shader for after the trace ray finishes. So here's an example. Like you split it into the first part. You push all the variables that live across onto the stack. Like we use Scratch. In practice, that's just another region of VRAM that we also use for like spilling registers and stuff like that in our compiler. Push the shader ID of resuming, and then next shader is the trace ray shader, and then at the end of it, at the resume, like we pop everything off and set the next shader from popping stuff off from the stack. And then we do the big loop and switch case on the shader ID. So like we do all these callbacks and we win nothing by it. Essentially, we get to push a bunch of stuff to a stack, which is VRAM. We have a big switch, which in near a switch ends up being essentially a bunch of if and else because there's no native switch. And that's what we have. And this is not meeting expectations. This is the biggest blocker why we're not saying, okay, ray tracing is fully done. That's because ray tracing also has pipeline libraries. Because, of course, you don't know all the materials at all at the front of things, so you want to add materials later. And of course, pipeline libraries come with the idea that you actually compile your stuff when the pipeline library is created and not when the final pipeline is created. That doesn't work well with that central big loop with switch because we compile everything when the pipeline is compiled. And that results in huge stutters and stuff. So ideally, we have an indirect branch instruction that we'd like to use, but we need to do a bunch of echo work for this. The nice part about the previous approach of just doing the big loop and switch is this didn't need any echo changes at all. It was basically all linear. And then, yeah, the problem with any kind of control flow is it's still a SIMD machine. So it was kind of implicit, but like you have a huge potential for divergence, like because you can only execute one kind of one shader at a time. So if every lane has a different shader, that's going to be messy and you're going to be not very efficient. And then we can compile things separately, but this needs echo changes, not only for the indirect branch, but we also did a lot of optimizations like, hey, only include certain bits in your shader ABI if they're actually used. But now because you're calling an unknown shader, you don't know what's actually used. So that's what we're working on. And then now, what's the current status? So ray queries are enabled by default. That was the simple option. And ray tracing pipelines are behind the environment variable. radv test equals RT. As said, separate compilation is kind of the main blocker there. And we have a couple of working games. Quake RTX is a simple demo. We have Control, we have Deadloop. I hear Resident Evil Village works and Metro Exodus. Okay, I might have that wrong. I think it's Enhanced Edition. I'm sorry. Works. There's also a bunch that doesn't work, like Doom Eternal runs but doesn't have the reflections right. And there's a whole bunch of DXR 1.1. So DXR is the direct 3D equivalent, and like there's a 1.0 and the 1.1 version, and we don't have all the Vulkan features for 1.1. So there's a whole bunch of more recent ray tracing games that we don't support yet. Performance-wise, so I have benchmarks here. I'll take AMD GPU as the baseline here, and we actually see that upstream as of now is very bad, hitting about 40% of the performance. And experimental, so experimental is with a better BVH build. We're getting much closer, 60 to 70%. And funny part here is that AMD VLK, so that's kind of AMD GPU Pro with LVM instead of their proprietary compiler, is much slower than AMD GPU Pro as well. So in the ray query path, we actually get quite close, within 10%. So obviously there's still a bunch of work to do here. And we have integration with RDNA Analyzer. So this is a tool from AMD that basically allows you to visualize your BVHs and look at, hey, what are expansive parts of your scene and not. And this is actually pretty cool to see how poor BVHs are. Or at least I made this one with the experimental BVH builder. And we actually had two new contributors who kind of came out of nowhere and did really cool stuff, like the RDNA Analyzer integration or the ray query implementation. So they've been pretty active, and I'm very happy and thankful for that. And then what comes next? Yeah, so on the feature side, separate shader compilation is a big thing, because then we can enable ray tracing by default. And indirect BVH build, so where like a lot of the parameters also come from like a GPU buffer that's not known at recording time, which is needed for DXR 1.1. Performance-wise, we need better BVH building. We need to land that. Like I said in the nodes overview, like we can do multiple triangles per node and 16-bit floating point node bounds, which we're totally not using at all. So we can do a lot of more optimization there. Although initial benchmarking has shown that that's likely less than a 5% improvement in ray tracing performance. Micro-optimize the hell out of the transversal loop even more. I mean, it's a pretty tight loop. I think we're doing about 70 factor ALU instructions per iteration right now. And I'm trying to remove every one of them. And then optimize it. So the main loop, like for the callback structure, we haven't really optimized at all. And there's ideas we could do there, like we could find duplicate shaders or resume shaders. Like I expect a lot of them will, for example, hey, we do a trace ray and nothing after, so we really didn't need to split the thing. We can just call and then go jump 2 stack frames at once, for example, or tail calls, that kind of stuff would be a pretty nice thing. And yeah, AMD has announced or announced that they will announce their next generation of GPUs later this year. So who knows what interesting new ray tracing features that will bring that we can integrate in this process. Let's just hope I don't have to rewrite everything again. And that was it. Thank you all. Any questions? Jason?
No, we will get to it later. For the stacks, since you only have a 4-bit area tree, have you considered just packing it all into like a 32 to 64-bit integer and bit shifting to do your indexing instead of having to do memory scratch?
For what? For
your stack indices in your BBH.
Yeah.
Can you repeat the question?
So for the stack indices in the BVH walk, have I considered using 32-bit indices?
A 32-bit integer and just storing 2 bits per stack level.
Okay, so the question is like whether I've considered using 2-bit indices in my stack. So that was a consideration. We found several papers also about like essentially like restarting your search like once you flow out of your search stack. So the main consideration there to not do it was because then we still, like even though the space is much smaller, you still have a limited stack depth. And most of the algorithms we found for like building a BVH had no consideration for the depth at all. So we thought like it would be a way easier integration if this was something we just didn't have to worry about. And like when you have those 2-bit indices, you're still kind of dealing with the either restart or backtracking. So like you still want a short stack in combination with that. That's like a normal stack. So that would be pretty similar. Alisa? I actually don't know. I suspect not the most important point right now. Oh, right, yes. So with the ray tracing pipelines, how bad is this for the instruction cache? And I don't know. I haven't benchmarked it, but I suspect it's not our most pressing issue right now. It does result in huge shaders, though. Like, I think one of the few games that we have not working is because of a compiler crash because the shader is too big. Yes.
I've done a lot of stuff with PDHs for like physics and stuff like that. And the general advice there is always first stuff, so you can kind of do like batches of stuff more efficiently.
Yeah.
It's just not applied for some reason.
Yeah. So the question was whether like having worked with BVHs a lot, the idea was always to do breadth first and then batch a lot, and a bunch of things like API limitations make it hard to batch here. So we haven't done that, and then like breadth first does result in a ton of memory bandwidth that makes it not worth it. Like if you can't batch. So I think that's what it mostly comes down to. It's one of the big limitations here that like we have no great hardware options to like, especially in the ray tracing pipeline. Like you saw Intel, who has like great hardware on like when you have lots of different things like change things between different work groups and stuff like that, and we have no great options there. So like we need a bunch of software machinery that we have to try to get fast to move things around, which is going to be a big limitation also with like avoiding divergence in things. So I'm still looking for options there. It's not our most pressing issue right now. Like a couple of games I checked, like the active lanes for the ray tracing, like at the start of the ray trace, are about 80%, which is not too bad. But it's definitely a concern, especially as you go more and more indirect rays. Yes.
So about building deviations, what extent is that a finished research program right now? Is it mostly that probably for you just the implementation that's the challenge, or both the research and the implementation?
So okay. So the question was whether, like, how much of BVH building is like finished research and just implementation, or whether there's actually stuff to look at. I think it's a combo. So BVH builds, like, at its core is like fairly well researched. There are a ton of papers on the field, though there's a bunch of like details about like, hey, you have a split BVH because you have this 2-level acceleration structure, and there's stuff like that we can do. Like there's the theory, and there's the like what kind of stuff can we tweak to actually make this the fastest thing possible. But yeah, we're mostly still in the let's get an algorithm implemented correctly.
Why is it that Kronos decided to leave the implementation of BVH building to the driver rather than to the application developer?
The follow-up question is why Kronos left the BVH building up to the driver rather than the application developer. So I have two speculative answers that I'm saying because I don't want to say anti-Kronos, and then Jason can probably talk about the Kronos things afterwards. So first things first, the BVH format is hardware specific, so like you don't really know. Second thing is we want direct 3D hardware and software compatibility, and that does it the other way. But those are my speculation. I see Jason nodding, so I'm assuming I got it.
Yeah, so the big reason is that the format is hardware specific, and we want to keep it that way so that we can continue to mutate the format over time. It may eventually be something like press textures, where we have standard BVH formats that you can just, read off of disk or something. But at the moment, there is enough. This is still enough of an R&D space that we don't want to lock the formats down, to give implementation freedom to do what they need to do to make things happen.
Okay, so to repeat, Jason, like he basically confirmed that yes, it's going to be hardware specific, and Kronos didn't feel like locking it down just yet, as it saw more evolvement in the space for now. And
yeah, we have a question from the live audience. How difficult has it been to debug issues in RT shaders? And have you discovered any useful tips or tricks?
And have we discovered any
Useful tricks or tips?
It's been pretty hard, mainly because like a lot of it is very indirect. Currently, we don't have a lot of experience with it. Mostly the games that worked are games that worked when we implemented all the features. There's been a bunch of things. A big limiter there, though, is that RenderDocs doesn't support ray tracing at this point. So, like, when we want to debug something, like, we basically have to do our own custom dumping of what we think it should do. experimentally, I want to try using something like gradient race analyzer to see part of it, and then if we can maybe dump race or something, that would be nice. But yeah, that just needs a bit of dumping. And to make dumping easier, Hans Christian on the VKD3D side implemented a bunch of dumping that I want to port over to radv, which I think is roughly a shader print kind of thing. And if we have that reusable, it would be way nicer to reuse that as we debug different bugs. Any other questions? Then let's leave it here. Thank you all.